We are in section 9.3, hypothesis testing for a population mean, standard deviation unknown, right? This is analogous to what we did last time, except that before, last time, we knew sigma, the population standard deviation, and in this case, we don't. Last time, what we did was we were given a random, or I should say maybe we took a random sample of size n and a sample mean x bar and a population standard deviation sigma. Now, again, that was somewhat unrealistic. A lot of times if we're estimating the population mean or trying to figure out whether a certain value is reasonable, we probably don't know the population standard deviation. But sometimes we do. We're going to look at the case today where we don't. All right, so we still have a random sample. We still have a sample mean. And in this case, we have a sample standard deviation S. Now, as before, the procedure is nearly the same, except we use the student's t distribution. With t alpha over 2 as our critical values to find our p-values instead of using z-scores from the normal distribution, right, from the standard normal distribution, okay? So to perform a hypothesis test when sigma is unknown, we do the following. Oh, and one quick thing before we begin, I'm saying critical values right here. This is also known as the test statistic. Right, last time when I wanted you to find the test statistic, I wanted you to find z. Here, if I want you to find the test statistic, I want you to find t. Okay? So anyway, what are we going to do? We're going to state the null and alternate hypotheses. Null means that the mu equals something, right? The population mean mu equals a certain value. Alternate hypothesis is that it doesn't equal that value, or it's less than that value, or it's greater than that value. That's one of those things, right? Next up, you find your standard error, which is your sigma over root n. And then the test statistic t, or t alpha over 2 as the book calls it. We then find the p value corresponding to your t-score with n minus 1 degrees of freedom. Determine your level of significance alpha and compare the two. Compare p and alpha. If p is less than or equal to alpha, then reject the null hypothesis. If not, then fail to reject the null hypothesis. Now, again, I don't love the double negative, but it's important that we use that language because statistical studies don't prove a positive. They just disprove a positive or fail to disprove a positive. That's how it is, right? And then, of course, state your conclusion if necessary, blah, 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 blah. This is very analogous to what we did last time, right? The difference is that we have slightly different procedure for numbers 2 and 3, right? We have degrees of freedom. We have S instead of sigma. We have T instead of Z. Otherwise, it's just the same procedure, right? Now, a couple of requirements. The sample must be random, of course. The sample must be large and greater than 30, or from a population that is roughly normally distributed, right? This is because of the central limit theorem, right? CLT says this, right? All right, just remember, this is from the right. Central limit theorem has conditions for when the sampling distribution is normal, right? So anyway, let's take a look at this. You can pause to check out the prompt for example 1. Just a couple of bits that we're highlighting right here. This is the estimated population mean. We have a random sample of n equals 55. This is your sample mean. This is your sample standard deviation. And then they're wondering if LA doctors make more on average than the national average, right? So if we look at our null and alternate hypotheses, we're getting, for the null hypothesis, that mu equals $178,258. Note that the alternate hypothesis has nothing to do with our sample statistic. We could have come up with our alternate hypothesis before we even took our sample. Okay, there are our hypotheses. Now we compute the value of our t-statistic. How many degrees of freedom are there? Well, let's do the easy part first. Degrees of freedom equals n minus 1. So we're done with that. I entered the stuff into Excel. Right, our sample data, our sample number, right there's our degrees of freedom just to make sure. We also do need to enter in our hypothesized mean. Right, it's important to enter that in. You don't need to worry about your significance level right now. You can just leave that at whatever. But once you enter that in, we get our desired answer, or we get an answer for our test statistic. And we'll just stick that right over here. And so we get that t equals 2.4638. Remember, t-values should be somewhat similar to z-values, right? If you're getting t as values that are really, really high in the double digits or whatever, you probably forgot to change your hypothesized mean. Okay, but anyway, so this is the test statistic. Okay, now let's state our conclusion. You don't need to enter this into Excel. You don't need to do that. It's not going to change the test statistic. All you need to do is take a look at your p-values, right? And in this case, our p-value for our corresponding alternate hypothesis is 0.0085. So since, and again, I'll just highlight this right here. Right, look at these guys. Okay, so since p equals 0.0085, which is less than alpha, which equals 0.05, we reject the null hypothesis. So we conclude that, what do we conclude? We do conclude that LA doctors do make more annual salary than the U.S. average, right? Which is good because it's, more expensive to live in LA than it is to live in most parts of the U.S. Right? Geesh, 178,000. And why didn't I become a doctor in LA? Because I'm a math professor, which is the greatest job ever. That's why. Anyway, would our conclusion have changed if we made our significance level 0.01? No. Right? Why? Because, well, maybe let me just move this over here. Because p equals 0.0085, which is less than 0.01. What about alpha equals 0.05? Oh, goodness gracious. Well, I'm going to go ahead and duplicate and say, well, I guess if alpha equal 0.005, maybe I'll make this pop and say yes, would have changed because p equals that, which is greater than 0.005. Okay. So again, note that our problem-solving process used, well, not Minitab, it's really Excel. Except we selected, well, one sample T instead of one sample Z. right? Just like before, just like with confidence intervals, right? In fact, this process is completely analogous to confidence intervals, right? Now, which situation is more realistic? Sigma known, sigma unknown. I already kind of mentioned this. Sigma unknown is usually, I'll say, more realistic. I'm sure there are cases where you know the standard deviation, but somehow aren't sure about the population mean. I'll say it's more realistic as we are I'll say we're testing reasonable values of mu. So if, I'll say, one parameter is unknown, then the other usually is also unknown. Okay. And of course, oh yeah, we can go ahead and just get rid of this. Say, oh, let's do one by hand using charts. No, we're just gonna keep using Minitab, okay, or keep using Excel, okay. So let's take a look at this. Economist wants to determine whether the mean is lower than the cutoff of 720, right? 720 being good. We sampled 100 people, and the mean score was 703, a little bit less. Standard deviation of 92. Again, unless it's clear that it's the population standard deviation, assume that it's the sample standard deviation. And again, they're just emphasizing, is this less than 720? And we've got that level of significance. Okay. So first off, let's state our hypotheses, right? Mu equals 720. Alternate hypothesis, mu is less than 720. Okay? Based on the sample, what can we infer about the population? So next up, well, they didn't actually ask us for the test statistic or the degrees of freedom, so we don't need to enter them. So I'm just going to go ahead and go in here and enter our stuff, right? Our sample mean was 703. Sample standard deviation was 92. Sample size, was that 100, I think? Yeah, 100. And our hypothesized mean was 720. Remember, it is important to put that in. So our test stat is negative 1.8478. Okay, whatever. We're interested in this one. And we have 0.0338. That's the p-value that we're interested in. So if we go ahead and just sort of stick this in here, we see that since p equals 0.0338, which is less than alpha equals 0.05, we reject the null hypothesis and conclude, what do we conclude? That the mean, the mean FICO score is less than 720. Bummer. Okay. Now, I've said before that that when we do hypothesis testing, we're doing the same thing as taking a confidence interval, just kind of saying things a little differently. And you might notice that when we do our stuff in Excel, we're using the same pages that we used for confidence intervals, right? Here's the connection. We reject the null hypothesis if and only if the hypothesized value of mu is outside our confidence interval. And that is, we fail to reject the null hypothesis if and only if the hypothesized value for mu is within our confidence interval. Right, here's just a quick little illustration of what's going on here. This is sort of one case of what can happen. Right, oh, that was so close. All right, there we go. It's as good as my standard normal curve is getting. Right, this is our sample mean point estimate x bar. And if we suppose that, let's say, alpha equals 0.05, then we have a situation where we have a confidence interval. Go out a little further there. And we have that. Now, depending on the situation, it could be that this area is 0.025 and this area is 0.025. This right here is going to be 0.95. Whoop, 0.95. And we're rejecting the null hypothesis when our value effectively corresponds to something outside our confidence interval. Okay. Now, this is doing a two-tailed test, right? Another situation could be we could have something analogous where, we've got a situation like this, and if we did like a left-tailed test, right, then this is just an area of 0.05, and this is an area of 0.95. And, of course, you could have another situation where this is our standard normal curve, and this value to the right is 0.05, and this value here is 0.95. Okay. All right, let's take a look at one more situation really quickly. You can pause to take a look. Looks like we are given a sample of size 14, 397, standard deviation that. It is important to note that the population is approximately normal. Can we conclude that this differs from 3,500? So again, state our hypotheses. Mu is going to equal 35,000. Make sure you know which mean is your hypothesized value and which is your sample mean. And because they use the word differs, that's what we're getting. Right, that's our ultra hypothesis, okay? Compute this t statistic. Well, we're just going to enter our stuff in, right? N equals 14, 37.9, and 7,200, right? So 37.9, 7,200, and 14. Hypothesized mean was 35. And so we get that test statistic. We're right there. And we're just going to quickly copy this in. Maybe stick this over here. And we'll say, I guess we'll just say for part B is our test statistic is t equals 1.5071 and degrees of freedom equals 14 minus 1, which equals 13. Now here we get that our p-value equals 0.1557, which is most definitely greater than alpha equals 0.01, we fail to reject the null hypothesis. So we conclude there's I'll say insufficient evidence that tuition and fees, maybe I'll say that private tuition and fees in CA differs from $35,000. And that's all.